All right, so today we're going deep on deprotonation. You know that chemical process?
Yeah, the deprotonation.
Might sound kind of intimidating at first, but I think it's actually pretty fascinating stuff.
Oh, for sure.
And it's way more relevant to our everyday lives than you might think.
Definitely.
So to help us navigate this, we have this great article from Assay Genie called Deprotonation, Unveiling the Chemistry Behind It,
Okay.
written by Umang Tyagi.
Cool.
So maybe just to start, like, what even is deprotonation?
Well, you can kind of think of it like, imagine a molecule is holding on to something super valuable, like a winning lottery ticket. Right.
Okay, I like that.
So deprotonation is that molecule giving away that ticket, which in this case is a proton,
So it's losing a proton.
which is just a hydrogen ion.
Okay, so like a tiny positive charge.
Exactly.
But wouldn't it want to stay neutral?
Well, it seems counterintuitive, but
Yeah.
sometimes losing that proton actually makes the molecule way more stable.
Really?
Yeah, it forms something called a conjugate base, which, even though it's negatively charged, can actually be more stable than the original molecule.
So it's not always about being neutral. It's more about, like, finding the right balance.
Yeah, exactly. Like, think about distributing weight evenly in a boat. If it's all piled up in one spot, it gets unstable, right?
Makes sense.
So in a molecule, how that charge is spread out plays a huge role in how stable it is.
Okay, I see. So, like, how does this play out in an actual example?
So let's take acetic acid. It's the stuff that makes vinegar taste,
Right.
tangy. When acetic acid loses a proton, it turns into acetate ion. And because the negative charge is spread out or delocalized over a bigger area, it's actually more stable than the acid form.
Huh, that's really interesting. So by losing a proton, it actually becomes more balanced and stable.
Exactly.
Cool. But I guess, like, why should we care about this? This is all happening at such a tiny scale.
Well, because deprotonation is happening all the time, all around us. It's like the engine driving tons of reactions in our bodies, in nature, and in labs.
Oh, wow, I see. So the article mentions acid-base chemistry, which affects everything from the pH of soil to, well, like we said, vinegar.
Right. And think about soil pH, for example. That impacts how well crops grow.
Oh, that's true. So it's not just theoretical, it has real-world implications.
Right.
What else does the article talk about?
Well, there's organic synthesis. That's basically building new molecules from scratch.
Oh, right.
Like, it's how we get medicines, materials, all kinds of stuff.
And that needs deprotonation.
Definitely. Think of it as like activating molecules, getting them ready to react and form new bonds.
Okay, so without it, we wouldn't have a lot of the products we rely on.
Exactly.
Wow, that's incredible. I didn't realize it was involved in so much. The article also mentioned biochemistry, like enzymes.
Yeah, enzymes are like tiny machines, basically, speeding up reactions in our bodies. And guess what? Deprotonation is often a key part of how they work.
So this one process is fundamental to life itself. It's kind of like deprotonation is the key that unlocks all these possibilities, from like tiny biological processes to making brand new materials. It's wild. But how do scientists actually make deprotonation happen? Do they have some kind of like a deprotonation ray gun?
Not quite a ray gun, haha, but they do have a pretty impressive toolkit, I guess you could say.
Okay.
The article lists some of the methods and reagents.
Yeah, it was like reading a spy novel with all the code names, honestly.
Yeah.
Strong bases, Grignard reagents, metal hydrides.
Right. It does sound pretty intense. And well, each one has its own specialty. For instance, strong bases are like, I guess you could say they're like molecular wrecking balls. Super reactive. They can rip a proton off of pretty much any molecule.
Okay, so brute force. What about those, they call them proton sponges?
Oh, yeah, those are cool. They're more like specialized vacuum cleaners for protons. They can be used to very selectively remove them.
So it's more precise.
Exactly, like a molecular scalpel.
I see. That's amazing. And how about the metal hydrides? Those sounded pretty powerful, too.
Yeah, metal hydrides are more like, I guess, molecular matchmakers. They help facilitate specific deprotonations, helping to carefully pair up molecules for reactions.
It's incredible how much control they have over this process. Like
Yeah.
manipulating molecules at such a tiny scale. It's mind-boggling.
Yeah, it is. And that ability to, manipulate matter at such a fundamental level, I think it raises some interesting questions.
It's like we've been given the keys to the molecular kingdom, but what we do with that power is a whole other conversation.
Exactly.
Before we go there, maybe let's explore some specific ways deprotonation is being used
Oh, sure, yeah.
to actually shape our world. We've talked about the what, but I'm curious about the how.
Right.
Like, where do we see deprotonation in action?
Well, one area the article mentions is material science.
Okay, material science.
Mhm.
I don't know much about that, to be honest.
Ha.
What's the connection to deprotonation?
Well, deprotonation is a key tool in material science because it lets scientists modify the properties of materials at the molecular level.
So they're like fine-tuning materials
Mm,
by manipulating their protons.
exactly. By removing or adding protons, you can change how molecules interact with each other,
Wow.
and that can affect a material's strength, flexibility, conductivity, all kinds of things.
So it's like they're using deprotonation to create materials with, like, superpowers.
Haha, you could say that. Like, for example, deprotonation can be used to create polymers with specific properties.
Polymers, right. Those are used in everything from clothes to electronics.
Exactly. They're long chains of molecules. And by controlling their structure through deprotonation, scientists can create some pretty amazing materials, like super strong plastics, waterproof fabrics, even self-healing materials.
Oh, wow. That's incredible. It's amazing how, like, manipulating something as tiny as a proton can have such a huge impact on the materials we use every single day.
It really shows how even the tiniest changes at the molecular level can have these ripple effects on the world around us.
Definitely. So we've talked about agriculture, materials science. What other fascinating applications are there?
Well, one thing that caught my eye was phase transfer catalysis.
Okay, I'll be honest, that sounds kind of intimidating.
Yeah, it's a bit of a mouthful.
Can you break it down for me?
Sure. Imagine you're trying to mix oil and water. They don't really want to cooperate, do they?
Not really.
Well, a lot of chemical reactions involve reactants that are soluble in different solvents, like, oil and water, and they need a little help to mix.
So how do you get them to react if they're in separate phases?
That's where phase transfer catalysts come in. They basically act like molecular translators, I guess you could say, allowing reactants that wouldn't normally mix to interact and react.
So it's like building a bridge between the oil and water, allowing them to, like, mingle and actually react.
Yeah, exactly. And often deprotonation reactions, they involve reactants that are in different phases. So phase transfer catalysis can bring those reactants together, enabling the deprotonation to happen and making the reaction way more efficient.
Huh. It's amazing how chemists have developed these techniques to, like, overcome the challenges of working at the molecular level.
It really is. It's a testament to human ingenuity, I think, and our desire to understand and manipulate the building blocks of, well, everything.
That's a great point. But I think, as we delve deeper into these techniques and the power they offer, I think it's crucial to also consider the ethical implications.
Oh, absolutely.
We've been focusing on the how, but maybe it's time to shift gears and think about the why.
Yeah.
Like, what are the potential consequences
Yeah.
of our ability to manipulate matter at such a fundamental level?
That's a big question. I think it's crucial to remember that science doesn't exist in a vacuum. Every scientific advancement, including our understanding of deprotonation, it has the potential to impact society in some pretty profound ways.
Right, so it's not just about the science itself, it's about thinking through the potential consequences.
Exactly, both good and bad. We need to ask ourselves, who benefits from these advancements? Are there any risks? How can we ensure these powerful tools are used responsibly?
It's like we're holding a magnifying glass that can focus incredible power. We need to be really careful about where we point it.
That's a great analogy. Take medicine, for instance. Deprotonation is crucial in developing new drugs. But as we create these new drugs, we need to think about their effectiveness, sure, but also their potential side effects, accessibility, affordability.
It's a multifaceted issue. It's not just about making a cure. It's about making sure it reaches the right people.
Yeah.
And that it doesn't create, unintended consequences.
Exactly. And that same logic applies to other fields, where deprotonation is playing a bigger and bigger role, like material science.
Right.
As we develop new materials with these incredible properties, we need to think about their environmental impact, their sustainability, even their potential for misuse.
Yeah, that makes sense. Like, a super strong plastic might be revolutionary, but what happens when it ends up in a landfill? Or what if a self-healing material leads to products that are designed to last forever? That could lead to overconsumption and waste.
Exactly. Those are all important questions. We need to approach these advancements with a critical eye, understanding that every innovation, it has the potential for both positive and negative consequences.
It feels like we're entering this era where Scientific progress is just accelerating.
Yeah.
It's more important than ever to have these conversations about ethics.
I completely agree. And it's not just up to scientists to have them either. It needs to involve policymakers, ethicists, the public.
Yeah, we all have a stake in shaping the future of science and technology.
Absolutely. And it's a future that's being shaped in part by our growing understanding of things like deprotonation.
It's fascinating to think that, this one tiny process, the removal of a single proton, it has the potential to unlock so much, but also to raise such profound questions.
It really highlights how interconnected everything is. Science, ethics, society.
Well, this conversation has certainly given me a lot to think about. It's a reminder that every breakthrough comes with responsibility.
Definitely.
Now, before we wrap up, I wanted to go back to something from the article. It mentioned how deprotonation helps us understand how acids behave.
Oh, right. Acids, they're fascinating. And deprotonation is really at the heart of what makes them acidic.
Yeah, I remember from high school chemistry that acids donate protons, but I never really understood what that meant, at a deeper level.
Well, remember that analogy of the molecule holding the winning lottery ticket?
Yeah.
An acid is like a molecule that's super eager to give that ticket away, that proton.
Okay.
And when it does, it forms its conjugate base.
So the more willing a molecule is to give up a proton, the stronger the acid.
Exactly. It all comes down to how tightly that proton is held. Strong acids, like hydrochloric acid, they donate protons really easily. But weak acids, like acetic acid, they hold on more tightly.
And deprotonation is the process of that proton being handed off.
Precisely. And the strength of an acid is directly related to how easily it undergoes deprotonation.
So understanding deprotonation is key to understanding acidity.
Absolutely. It helps us predict how acids will behave, how they'll react, how they'll impact their environment.
That makes a lot of sense. But what determines how easily an acid gives up a proton? Like, what makes some strong and others weak?
That's a great question. And it all has to do with the stability of the conjugate base, the one that forms after deprotonation. Remember, molecules are always trying to be as stable as possible.
Right, like finding that balance.
Exactly. If the conjugate base is very stable, the acid is more likely to give up its proton because, the whole molecule becomes more stable after deprotonation.
So it's like a trade-off.
Yeah, you could say that.
The acid sacrifices its proton in exchange for stability.
Exactly. And how stable that conjugate base is. It depends on a few things, like the electronegativity of the atoms involved and how well a negative charge can be spread out.
So it's not just about the acid itself, it's about the whole system.
Right, how the acid and its conjugate base interact.
It's a delicate balance.
It is.
And understanding that balance is crucial to understanding how acids behave.
Definitely.
This is starting to make a lot more sense now. It's like we're zooming in and seeing this intricate dance of protons, acids, and conjugate bases. It's happening all around us.
And it's a dance that's fundamental to so much, from digesting food to creating new materials.
Wow, that's pretty amazing. To think that something as simple as the transfer of a proton
Yeah.
can have such a huge impact.
It really goes to show you the most fundamental processes are often the most powerful.
I think we've covered a lot of ground today. We've explored the what, the how, and the why of deprotonation, its applications, implications, even its role in understanding acids. Is there anything else you think we should touch on?
Well, it's interesting that you mentioned the simplicity of a proton transfer. It reminds me of something else the article talked about briefly, hydrogen bonding.
Oh, right, hydrogen bonding.
Yeah.
I vaguely remember that from chemistry class. Something about weak bonds between molecules.
Exactly. And they are unbelievably crucial. They're responsible for so much, from the properties of water to the structures of DNA and proteins.
Wait, really? So the building blocks of life rely on these, seemingly insignificant bonds?
Absolutely. And here's the even crazier part. Deprotonation can actually influence hydrogen bonding.
Hold on, how does removing a proton affect those bonds between molecules?
Okay, so think about it this way. When a molecule loses a proton, it becomes more negatively charged.
Right.
That increased negative charge can make it more attractive to other molecules with a slight positive charge, like those with hydrogen atoms involved in hydrogen bonding.
So it's like deprotonation creates this molecular magnetism, strengthening those weak bonds.
Yeah, that's a great way to put it. It's like turning up the volume on those interactions, and that can change a molecule's shape, its properties, how it interacts with other molecules.
Wow, so even subtle changes at the molecular level, like removing one proton, can have these cascading effects.
It's a beautiful example of how interconnected everything is at that level. It reminds me of that quote. Eventually, everything connects people, ideas, objects. The quality of the connections is the key to quality per se.
That's a great quote. And it perfectly captures what we've been talking about. These connections, these seemingly simple processes like deprotonation, they're the foundation for so much complexity in the world.
Exactly. And as we continue to learn more, who knows what we'll discover? It's a really exciting time to be exploring chemistry.
This deep dive has definitely been an eye-opener for me. I feel like I have a whole new appreciation for chemistry now.
That's great to hear. And it's a field that's constantly evolving. There's always more to learn, more connections to find.
Well, I want to thank you for joining us on this journey. You've been a fantastic guide.
My pleasure. And to our listeners, if you want to learn more, we highly recommend checking out the full article from Assay Janie. We'll include a link in the show notes.
And as you explore and learn about deprotonation, remember to stay curious, keep asking questions, and never stop being amazed by the molecular world.
Because even in those tiny interactions, like the transfer of a single proton, there's a universe of wonder and possibility.
Beautifully said. And on that note, we'll wrap up our deep dive into deprotonation. Until next time, keep those brains buzzing. Okay, so we're back and ready to keep going with our exploration of deprotonation. Before the break, we were just starting to get into some of the ethical considerations, the ones that come with being able to manipulate matter at the molecular level. Where do you think we should start with that conversation?
Well, I think it's important to remember that science isn't happening in isolation. Every advancement, including our understanding of deprotonation, it has the potential to impact society in big ways.
Right, so it's not just about the science itself, but also thinking about the consequences.
Exactly, both the good and the bad. We have to ask ourselves, who benefits from these discoveries? Are there any potential risks we need to be aware of? And how can we make sure that these powerful tools are being used responsibly?
It's like we're holding this magnifying glass.
Yeah.
That can focus a ton of power, but we need to be super careful about where we point it.
That's a great way to put it. Take medicine, for example. Deprotonation is super important for developing new drugs, right?
Right.
But as we're making these new drugs, we need to think about more than just how effective they are. We also need to consider potential side effects and things like accessibility and affordability.
Yeah, it's not just about making a miracle cure. It's about making sure that cure actually gets to the people who need it.
Yeah.
And that it doesn't create, other problems in the process.
Exactly. And the same goes for other fields, too, where deprotonation is becoming more and more important, like material science.
Right, material science, yeah.
As we develop these new materials with incredible properties, we need to think about their environmental impact, how sustainable they are, and, even the potential for them to be misused.
That's a good point. Okay, let's say we create this super strong plastic. That's amazing. But then what happens when it ends up in a landfill? Or what if a self-healing material leads to products that are designed to last forever? Wouldn't that lead to more consumption and waste?
Those are all valid concerns. We need to approach these advancements thoughtfully, recognizing that every innovation, every new discovery, it has the potential for both positive and negative consequences.
It definitely feels like we're living in a time where scientific progress is accelerating so fast.
For sure.
So having these conversations about the ethical implications is more important than ever.
I couldn't agree more. And it's not just a conversation for scientists either. It needs to involve policymakers, ethicists, the general public.
Yeah, we all play a role in shaping the future of science and technology.
Absolutely. And it's a future that's being shaped, at least in part, by our understanding of things like deprotonation.
It's kind of wild to think about. This one tiny process, removing a single proton, it has the potential to unlock so many possibilities.
Yeah.
But it also raises these really big questions.
Yeah, it really highlights how interconnected everything is. Science, ethics, society.
This conversation has given me a lot to think about. It's a good reminder that every scientific breakthrough comes with a responsibility.
Definitely.
So before we move on, I wanted to circle back to something that caught my attention in the article. It talked about how deprotonation helps us understand how acids behave.
Oh, yeah, acids. They're fascinating. And deprotonation is really at the core of what makes them acidic.
Yeah, I remember learning in high school chemistry that acids donate protons. But I never really understood what that meant, on a deeper level.
Well, remember that analogy with the molecule on the winning lottery ticket?
Yeah.
You can think of an acid as a molecule that's really eager to give that ticket away, that proton, and when it does, it forms its conjugate base.
So the more willing a molecule is to give up a proton, the stronger the acid.
Exactly. It all comes down to how tightly that proton is being held. Like strong acids, like hydrochloric acid, they donate protons really easily. But weak acids, like acetic acid, hold on to them more tightly.
And deprotonation is that process of the proton being, like, handed off.
Precisely. And the strength of an acid is directly related to how easily it can be deprotonated.
So if you want to understand acidity, you have to understand deprotonation.
Absolutely. It helps us predict how acids will behave, how they'll react with other things, how they'll affect their environment.
That makes a lot of sense. But what determines how easily an acid gives up a proton in the first place? Like, what makes some acids strong and others weak?
That's a great question. It has to do with the stability of the conjugate base, the one that forms after the acid loses its proton.
Mhm.
Remember, molecules are always trying to be as stable as they can be.
Right, finding that perfect balance.
Exactly. So if the conjugate base is very stable, the acid is more likely to give up its proton because the whole molecule becomes more stable after deprotonation.
It's like a trade-off. The acid gives up its proton to gain more stability.
Exactly. And the stability of that conjugate base, it depends on a few factors, like the electronegativity of the atoms involved and how well that negative charge can be distributed.
So it's not just about the acid in isolation. It's about the whole system.
Right, how the acid and its conjugate base interact with each other.
It's a delicate balance.
It really is.
And understanding that balance is key to understanding acids.
Definitely.
This is really starting to paint a clearer picture for you. It's like we're zooming in and seeing this whole intricate dance of protons, acids, and conjugate bases, and it's happening everywhere.
And it's a dance that's crucial to so many things, from how our bodies digest food to how scientists create new materials in a lab.
It's amazing to think that something as simple as a proton being transferred can have such a huge impact on the world around us.
It really shows you. Sometimes the most fundamental processes are the most powerful ones.
Well, I think we've covered a lot of ground today. We've explored the what, the how, and the why of deprotonation. We've talked about its applications, the ethical implications, and even how it helps us understand acids. Is there anything else you think we should touch on before we wrap up?
Yeah, it's funny you should mention that. The simplicity of a proton transfer. It makes me think of something the article touched on, hydrogen bonding.
Oh, right. Hydrogen bonding. Yeah, I kind of remember that from chem class. Something about, like, weak bonds between molecules.
Yeah, exactly. And those bonds are way more important than you might think. They're responsible for a ton of stuff, like the properties of water
Oh, okay.
and the structures of DNA and proteins.
Wait, seriously? So, like, the building blocks of life rely on these weak bonds?
Oh, yeah, absolutely. And here's the crazy part. Deprotonation can actually affect hydrogen bonding.
Whoa, hold on. How does taking away a proton change those bonds between molecules?
Okay, so think about it this way. When a molecule loses a proton, it becomes more negatively charged.
Right.
And that extra negative charge makes it more attractive to other molecules. Specifically, molecules with a slight positive charge, like those with hydrogen atoms involved in hydrogen bonding.
So it's kind of like deprotonation creates this, like, molecular magnetism.
Yeah, exactly. It's like suddenly those interactions are way stronger. And that can change molecule shape, its properties, even how it interacts with other molecules.
Wow, I see. So even tiny changes, like getting rid of one proton, can have these huge ripple effects.
It's a perfect example of how everything's connected at the molecular level. It reminds me of that quote, eventually everything connects people, ideas, objects. The quality of the connections is the key to quality per se.
Ooh, that's a good one. And it really fits with what we've been talking about. These connections, these simple processes, they're the basis for so much complexity in the world.
I know, it's pretty amazing. And as we keep learning more, who knows what we'll find? It's a really exciting time to be in chemistry.
This whole deep dive has been really eye-opening for me. I feel like I have this whole new appreciation for chemistry now.
Well, I'm glad to hear that. And it's a field that's always changing. There's always more to learn, more to discover.
Well, I want to thank you for joining us on this journey. You've been a fantastic guide through this whole world of deprotonation.
It's been my pleasure. And for our listeners, if you want to keep exploring, definitely check out the full article from Assay Genie. It's called Deprotonation, Unveiling the Chemistry Behind It. We'll be sure to link it in the show notes.
And as you learn more about deprotonation, remember to stay curious, keep asking questions, and don't forget to be amazed by, the molecular world.
Because even in the tiniest interactions, like transferring a single proton, there's so much potential and possibility.
That's a great way to put it. And on that note, we'll wrap up our deep dive into deprotonation. Until next time, keep those brains buzzing.